Hello, this is MA280 Multivariable Calculus. I'm Professor Wheatley. Today we're going to discuss functions of several variables. Okay, so we are used to the notation f of x equals y, meaning y is a function of x. That is the standard function notation we use for single variable calculus. That's a 2D case. All we're doing is extending it to a 3D case by making it some f of xy equals z. This is a function of both x and y, and that's the 3D case. So your canonical example, or at least a very simple one, might be, think about the growth of a certain plant referring to both the amount of sunlight it receives and the amount of water it receives every day. The amount of water is x, sunlight is y, growth is z. There's a function of two variables resulting in a third variable z. Okay, so in a more mathy example, say we had z equals x squared plus y squared. Well, we know that's the equation of a paraboloid in space. And in this case, z is the height, and it's a function of both x and y. All right? Okay, well, so even though I've put up here f of xy, a function of two variables, the fact is we can have as many independent variables as we want. So function can have as many independent variables as needed. And the fact is, in a real-life system, oftentimes we have lots and lots of things affecting the outcome. So we're going to have lots of independent variables. Okay? And the domain of these functions, so the domain D, is a set of ordered n tuples, right? Where n is the number of elements in the ordered pair or triple or quadruple or something. So, e.g., in a function of two variables, the domain consists of ordered pairs x, y. In a function of three variables, it would consist of ordered triples. So now you'd have three input variables. So you'd have input variables x, y, z, and you might have w being your output variable. Okay? However, even though you could have as many as you want to for independent variables, there's still, one and only one dependent variable. These are still functions, right? So every unique choice of independent variable gives you a unique value of dependent variable. And there is one unique value of it for each n tuple in the domain, right? So it's very possible that the ordered pair 2, 1 would give you a different output value than the ordered pair 2, 2. And over here, 2, 1 gives you a z value of 5, 2, 2 gives you a z value of 8, but each ordered pair produces exactly one value of z, okay? And these values of the dependent variable, so these values are the range R. So there's nothing different going on here from functions of two variables, or functions of one variable, excuse me. So everything else is analogous. The only difference is the domain sets are these n tuple sets. Okay, let's look at an example here. So we should recognize this formula. V of L, W, and H is the product of L, W, H. So this is volume of a rectangular box as function of length, width, and height, right? So there's the classical volume formula for length, width, and height of a rectangular box, all right? The domain set here, so the domain is all ordered triples, LWH, such that L, W, and H are all bigger than 0, right? We're just restricting that because you can't have any side of a box be 0 length or smaller. And the range here, the range is all reals greater than 0, which we'll denote as R bigger than 0, like that. So that's all real numbers bigger than 0. The volume must be a non-negative measurement, positive measurement actually. It can't be 0 either. Okay? Another one, so there's the volume formula. So more typically, we care about a certain surface in space. So maybe we have f of xy equals y squared minus x squared. Recognize that as a hyperbolic paraboloid. So this gives the height of the hyperbolic paraboloid as a function of its position in the xy plane, right? So it has some position in the xy plane. There's some point lying in the xy plane. And then the hyperbolic paraboloid is some surface that sits above the xy plane, and some points in it and some points below it. And the height of that surface is always given as a function of its position in the xy plane. Okay? And so the domain here is ordered pairs, xy. The domain is all ordered pairs, x comma y, such that, let's see here, x and y are real. There's no restriction on the domain here. We can plug in any values that we want to. And the range here is all real numbers. Range is all real numbers, since there's no reason why f of xy can't be arbitrarily big or small. If you want it arbitrarily big, for example, just set x equal to 0 and have your y be huge. Have it be some big positive number. It'll be very large, say 100, make it 100 squared will be the height. If you want it to be arbitrarily big and negative, just set your y equal to 0, make your x big, it'll be arbitrarily big, negative. You can make it small, make it close to 0, make it 0, whatever you want. Any real number is hit. Okay, so let's talk more about domain and range for a minute. And we're going to see that they are completely analogous concepts to functions of a single variable. So, domain and range restrictions are analogous to the single variable case. Right? In other words, we still can't go around plugging in negative numbers as square roots, dividing by 0, having negatives and natural logs, things like that. And our range restrictions follow suit as well based upon the behavior of the function. So, for example, say we had z equals root y minus x, like that. Well, the domain here, well, we can't have a negative inside the square root sign, so the stuff inside must be non-negative. So y minus x must be greater than or equal to 0. Okay, well, that means that y must be greater than or equal to x, right? And so what is this? Well, if you take a look at the xy plane, right, there's the line y equals x, right? On which side of it should I be shading here? Well, where is y bigger than x? Well, y is bigger than x over on this side. So all those points over there would be satisfying this inequality, and they would be in the domain set. So all the ordered pairs on this side of the line would be satisfying the domain set here. They would be valid points we could plug in over here and have things be okay. All right? And the range is going to be r greater than or equal to 0, since square roots can only produce non-negative results. Okay? So square roots can only produce non-negative results. Also, it's worth noting over here, too, that the line y equals x is also part of the domain set here because we do have greater than or equal to. Okay? So this line is also part of that domain set. Okay? Another one would be, let's see, so we can go down here, look at z equals 1 over x squared minus y squared. All right, well, the obvious problem here is we don't want division by 0. So our domain has to be such that x squared minus y squared is not equal to 0. Right? This means that what, x minus y, x plus y is how that factors. And that brings us down to what? X is not equal to plus or minus y, right? X is not equal to plus or minus y. So what we have here is, so the line y equals x, again, looks like that. The line y equals negative x looks like that, right? Well, in either one of those cases, we have a problem down here, right? We can't have those. So those lines are the only lines restricted from our domain set. Every point that doesn't lie on one of these two lines is a valid point to plug in down here. So these two lines are restricted. Any point that doesn't lie on one of those two lines is okay for the domain set. And the range here, the range ends up being r delete 0. You can't have 0 over there. 1 divided by anything can't be 0. All other points are going to be okay. Okay? So there's domain restrictions. Probably do one more here very briefly. Let's see. So what if we had a function of 3 variables? Let me get rid of this. In fact, I'll erase everything. So if we have a function of 3 variables, or any more really, everything still follows suit. Say we had w equals x, y, ln, z. Well, our domain here, remember, natural log, you can only plug in things that are positive to it. So our domain here is going to be z greater than 0. So if we draw our xy plane, xy, z plane, so there's x, there's y, and there's z. What we actually want, so our domain will be the xy plane. Actually, the xy plane won't be included in there because z has to be bigger than 0. So it'll actually be everything. So here's the negative z-axis. It'll be all points, the half space below where z is equal to 0. So think about it like this. Here's the xy plane lying here. Z is going up. Z is coming down. So here's xy. Z goes up. Z comes down. We only want everything that's going down. So the xy plane is not included because that's where z is 0. Everything below the xy plane extending down forever and ever is included. That's our domain space. And the range here will actually be all of R. So the range will be all of R there. Okay, so let's see what I want to do now. Get rid of this. And maybe we'll do one that's slightly harder. I don't know. So let's describe geometrically the domain of f of x equals square root y minus x squared. All right? Okay. So this is a little more complicated, but not so terrible. Our process is still the same. The stuff inside the root must be non-negative. So it's got to be greater than or equal to 0. All right? So the implication here is that y is greater than or equal to x squared. Well, again, we have the xy plane. There's the parabola y equals x squared. Well, that's in the solution set because the equality is here. All right? And then do we shade outside or inside? Well, pick a test point. So pick a test point, say that point right there. That's 0, 1. You put that into this inequality here, 1, 0 squared. The equality is satisfied, or the inequality is satisfied, I should say, right? So the test point works. Therefore, what you want is you want everything inside the parabola and also the parabola itself. This is going to be our domain set for this function, okay? So everything inside the parabola and the parabola itself will be the domain set, okay? So domain is parabola y equals x squared together with its interior as such. Okay, so let's talk about graphing now. Graphing and level curves. All right, so let's get rid of this. We talked about quadric surfaces a while back and graphing those, but in general, we want to be able to graph any surface that we feel like, at least some surfaces that we find are pretty easy to graph. So let's look at how we might do that. So this is graphs, level curves, and contours of two variables. Okay. So there you go. Okay, so we know that functions of two variables, well, they graph a surface in space. So they graph surfaces in space. So, all right. But what is often easier to us is to look at what's going on in the xy plane only and then kind of figure out how things would look when you add a z-axis in, because we're used to working in the xy plane, and so things there are easier for us geometrically to think about. All right, so another viewpoint is to look at curves in the xy plane. Okay, so definition. Let's see here. So the set of points x comma y in the xy plane, right, where a function of two variables f of xy equals a constant c. Right? So the set of points where f of xy equals a constant c is called a level curve of f in the xy plane. Okay? So the set of points where the function's height is constant is called a level curve in the xy plane. All right? Well, this is best seen by example, so in fact, let me clean up this so we can get some room to do this whole thing out. So, all right. So my function's going to be f of xy equals x squared plus y squared. We know that graphs a paraboloid already from what we know about quadric surfaces, but let's look at level curves and see why. So let's sketch several level curves and then graph the surface. Okay? Okay, so first things first, domain and range. Well, the domain is all of R. There's no restrictions there. The range is going to be R greater than or equal to 0, because when you add up two squares, you can only get something that's 0 or smaller. So this thing will lie entirely above the xy plane in 3 space. Okay? So we know the surface, like I said earlier, the surface is an upward opening paraboloid. All right, well, let's examine what the level curves look like. So consider, Remember, level curves are where the function's value is constant. And so we'd like to choose, I mean, we could pick any constant we want to here, but we'd like to choose constants that would give us nice level curves in the xy plane, not nasty ones. So here, things are kind of nice because any value we choose will not be horrible. But I'm going to pick level curves 0, 1, 4, 9, 16, and other perfect squares. Ask yourself, well, why would I do that? Well, think about what I've got then. I've got x squared plus y squared equals 0. All right, well, what is that? Well, it's the degenerate equation of a circle with radius 0. Well, that's the point 0, 0. That's kind of dumb, but, and then x plus y squared equals 1. Well, that's a circle of radius 1, centered at 0, 0. Equal to 4 gives me a circle of radius 2, centered at 0, 0. And you get the point of this here. So if I add x squared plus y squared equals 3, I get a circle of radius 3, equals 9, equals 9. I get a circle of radius 3, centered at 0, 0. So what have I got here? I got a series of concentric, i.e. same center point circles, centered at the origin. And let's see here, they're growing by 1 in radius each time, right? Okay, so let's see. Let me erase the top part of this. I'll draw the level curves up here, and then we'll draw the surface. So this is all the stuff we got so far. Let's draw our level curves. Well, our level curves are concentric circles. So let's see here. Here's the xy plane. All right. There's the point 0, 0. Excuse me. There's the circle x squared plus y squared equals 1. There's the circle x squared plus y squared equals 2. Equals 4, excuse me. X squared plus y squared equals 9, so on and so forth. So these level curves are expanding out, right? So imagine, remember, every time, so all the points on this circle, so this circle here, this is x squared plus y squared equals 1. Every point that lies on that circle in the xy plane corresponds to a height of 1, right? So imagine you have some point, 0, 0, right? You have a circle of height 1, a circle of height 2 lying above it in the plane z equals 2, height 3 lying above that in the plane z equals 3. So what do you wind up with? So let's see here. Let's put it like that. Let me move this over a little bit. So we want a paraboloid. All right, and then, so what have I got here? There's a circle, and does that look like a paraboloid? No, not particularly, no. Let's start again here. So let's start from the bottom and maybe try to work up. So there's the base of the paraboloid, and then maybe something that looks like that. Looks a little better, yeah, not terrible. So, and there's one parabola coming down, and it's going up like that, right? Yeah, there's your paraboloid. And then your axis is kind of sticking up like that, and there's z, right? So there's your paraboloid, x, y, and z, right? And this circle up here, circle quote unquote, this circle is, so this is the, how do I want to word this? So this is the circle x squared plus y squared equals c in the plane z equals c. In other words, the plane z equals 1 is a plane parallel to the xy plane that contains this circle, this circular cross-section. So these circles are rising up here. So imagine each of these rising up to a certain height, right? Each one getting higher and higher each time. Well, We have a bunch of circles that are concentric. They're forming this thing that's getting larger and larger with circular cross sections. That's a paraboloid like that. All right? So this is the plane z equals c. It has a circle x squared plus y squared equals c. Those circles are getting larger and larger. Our paraboloid is expanding out side by side. Okay? Okay, so one point of notation here. So level curves are curves that exist in the xy plane. So this is the xy plane, right? But I said that what's really happening here is that these circles are corresponding to these planes of certain heights that are cutting the surface. So a curve in space where the plane z equals c cuts the surface, it's called a contour curve. Contour curve, f of xy equals c, right? So I'm being a little bit notationally ridiculous here, but level curves exist strictly in the xy plane. Contour curves exist in various z-planes, all right? So what I mean by this, or what I mean by that is the following. So I guess I'll leave it up there for the time being. So i.e. the contour curve f of xy equals 4, well, that is the circle x squared plus y squared equals 4 lying in the plane z equals 4. In other words, here's the xy plane down here, okay? Up here is the plane z equals 4 parallel to the xy plane, and what's lying in it is this circle, all of which the heights are all 4, so the circle up in the plane z equals 4 is a contour curve. The circle lying in the xy plane is a level curve, okay? So as opposed to the level curve, f of xy equals 4, which is the circle x squared plus y squared equals 4 lying in the xy plane. So, I mean, that's sort of an esoteric point, and oftentimes you'll see them referred to in the same way. Contours and level curves are sort of referred to interchangeably with context defining what we're talking about. But still, it's important to know that there is a difference notationally, or at least meaning-wise, between them. Okay, so let's talk about functions of more than two variables for a minute. And the nice thing is that not a whole lot changes from our discussion of functions of two variables. So functions of three variables, However, what is different this time is that we no longer have to talk about level curves lying in the xy plane. Now we have level surfaces lying in the xyz plane. Okay, so f of xyz equals c is a level surface in space, right? Because now, when I have three variables, I'm graphing in 4D, which doesn't work so well on the whiteboard. That's for sure. But we can certainly, if we want to talk about a function of three variables, we can draw level surfaces, and then we can say, okay, well, how would it react if we had a fourth dimension going on? So here's an example. So suppose my function f of xyz equals x squared plus y squared plus z squared. Okay? Well, what does a typical level surface look like? Well, squared plus y squared plus z squared equals c. Well, what's that equation of? Think long ago, section 1. Now, this is the equation of a sphere. This is the equation of a sphere centered at the origin with, what have I got here? Radius root c, is that right? Yeah. Radius square root c. And this is for c bigger than 0. Right? Otherwise, we don't have any, there's no such thing as a level surface for that c less than 0. Okay? So we can make it c greater than or equal to 0, can't we? Yeah, because we'll just, when it's equal to 0, it's just the degenerate point 0, 0, 0. Okay? So let's see. So thus, what does the graph in 4D look like? Do I say? Yes, I do. In 4D is a series of spheres nested inside one another, right? So it's a series of spheres nested inside one another, right? And as we move away from the origin, the value of f of x, y, z, what am I saying here? Increases, yes, as the radii of the spheres increase, right? In other words, when we had the 2D case of the circles that were concentric, right? As we moved around a circle in the xy plane, we were stuck in a constant height z plane, right? As we walked around the circle, x squared plus y squared equals 1, we were stuck at a constant height. So this plane z equals 1, we walked around the circle, we're stuck entirely in that plane, right? Here, as we walk around the sphere, x squared plus y squared equals z squared, or plus z squared equals 1, excuse me, as we walk around that sphere, we are stuck at a constant value in the 4th dimension, right? But as we jump from sphere to sphere, that 4D coordinate goes up. So imagine, hard to draw certainly, but imagine you're on the sphere, x squared plus y squared plus z squared equals 1. You're walking around it. You're always at the same 4D coordinate. As soon as you jump to another sphere, say you jump to x squared plus y squared plus z squared equals 3/2, you've increased the 4D coordinate, this f of x, y, z coordinate, right? And as you move away from the origin, your spheres are getting larger and larger, right? Then your coordinate here in the 4th dimension is also going to get larger and larger, okay? And that's true in any direction that you walk away from the origin, because the spheres extend out forever and ever. So there's a sphere and a bigger sphere and a bigger sphere, and as you're walking away from the origin, your 4D coordinates getting larger and larger, okay? So it's worth noting here also, I guess, that your domain is all of R. I guess I really technically should say that your domain here is R, being sloppy here, it's R3, like that, set of all ordered triples with real coordinates. So set of all ordered triples with real coordinates. So I'm being a little sloppy. And when I said earlier that in the case of a function of 2 variables, your domain was R, it's really R2, set of all ordered pairs. And your range here, range with an N, your range here is going to be R greater than or equal to 0, right? So you'll always have a positive value of the 4D coordinate, right, or the 4D point, okay? Okay, so let's do one more of these. Let's change our function to not look like a sphere anymore, but instead let's make it f of x, y, z equals x plus z. All right, let's get rid of this. All right, so ask ourselves, what does a level surface look like here? Well, x plus z equals c. What is this? Well, we know it's the equation of a plane. It's the equation of a plane with the following characteristics. It has normal vector v equals I plus k, right? That's the vector normal to the plane, and passes through the points 0, 0, c. When I plug in x equals 0, that makes z be c, and c comma 0, 0, right? So this is a series of planes, right? Equal to various constants. They have the same normal vector, and they pass through these certain points. All right? So what's the graph in 4D look like? So the graph in 4D is a series of parallel planes. How do I say this here? Stacked, one on top of the other. One on top of the other. All right. So let's see here. All right. Let's draw an x, y, z axes. So maybe there's the point 0, 0, 1, and down here is the point 1, 0, 0. So now I'm saying my c is 1, right? I'm doing, this is x plus z equals 1. So my plane, let's see here. My plane's going to look like how? So I can connect those two up with a line like that. And my plane's going to have one of its sides parallel to that line. We're going to go to more than one color here to make this look better than it could. So one of my sides is parallel to that line. The other side is parallel to the y-axis, right? Okay. And then let's make life look good here. So that is all behind the plane. Let's see here. That is all behind the plane also. So what's happening here is what? So the plane, so this is actually, let's see here, this is behind, and that's behind. Yes, okay, so the plane is jutting out like that, right? So there's the x-axis coming out. That's behind. The z-axis is jutting out like that. So back here, it's behind, right? The y-axis is behind. It's coming out from behind there. So there's the z-axis coming out of the plane at that point. There's x coming out of the plane at that point. And then as your c's got larger and larger and more positive, your plane would have points up here and down here, but it would be coming out of the board forward like this, right? And as the plane, as the c got smaller and smaller, your x value would be back here, your y value would be down here, and your planes would be behind this plane, right? So they're going back into the board, right? So this may be the best drawing I've ever done up here. But okay, so is that it here? So, and this is a graph of the level surface f of xz equals 1, right? And that's about the best we're going to do for graphing 4D, certainly on a whiteboard. Okay, so that concludes functions of several variables.